Hello, and welcome to Week 6 of Digital IC Design with Dr. Mark Narden, class EE 423 at Oregon Tech. So in the first part of this week's topics, we'll be going through basically timing basics, reviewing that. We had done some of the basics a few weeks ago, but I'll review through that. Then going into more detail on timing, introducing the concept of logical effort, and then the delay in a logic gate, going through multi-stage logic networks, and how to choose the best number of stages and sizing of stages in order to get the best delay, and then going through example, and finally summary at the end. This is an outline of the beginning of this week. The second part of this week, I'll be covering basically wiring basically the wires in your design and how they affect delay and noise and other things. I'll go through more detailed outline of that section when we get to it later. So first part of the review of timing basics is just going through the types of delays that we can get in integrated circuits. Again, we introduced this before, but the propagation delay, keep in mind it's the maximum amount of time for the input to a given gate when it crosses 50% till the output crosses 50%. So while this is called propagation delay, it can also be called max time, and a lot of times I'll call it max time. At Intel, that's a very common. Usually we don't use propagation delay. We'll call something max time for the maximum amount of time that it takes for the delay through the gate, 50% input to 50% output. And then contamination delay is the minimum amount of time for the input from the input crossing 50% till the output crosses 50%. This is also called min time, and again at Intel pretty much we don't use contamination delay, we call it min time. So you will have like max time for input rising to output falling, or min time from input falling to output rising. It's basically the quickest delay is your min time, the longest delay is your max time. Then of course we have rise time. Rise time is the time for the output waveform, or well, any waveform really, but if we're talking about an output from a gate, for the output waveform to rise from, it starts at 0%, and as it crosses 20% mark, you start measuring the rise time, and the amount of time it takes to get from 20% to 80% as it's rising. This sometimes instead of being called rise time can be called the slope or the rising slope. Again, I'll use that a lot of times because at Intel that's the terminology they use, is they call slope instead of rise time. For fall time, it's kind of the opposite of rise time. It's the time for the waveform to fall. So if it's starting at VCC, when it hits the 80% of VCC on its way down, you measure the amount of time to get from 80% to 20% of its steady state value down to ground, and that will be called the fall time. Again, that at Intel a lot of times, we'll call it slope, and in the case of fall time it will be the falling slope. Sometimes you will have the average of the rising slope and the falling slope, or rise time and fall time. If you sum the two together, divide by 2, that can be your average slope, which could also be called your edge rate. So this figure here is just showing kind of graphically what we went through in the last slide. The top of the waveform, or top waveform, is the input to a gate. The bottom waveform is the output. When the input is rising and it crosses its 50% point, the output will eventually start falling. When it crosses its 50% point, if we measure the 50% to 50% time, that will be our propagation delay, or T sub PD for propagation delay, and the F is for the output falling. So the propagation delay falling is the 50% time from the input rising to the output falling. The slope, the falling slope or fall time, T sub F, is the time that it takes the output to fall as it's coming from VCC down 80 to the 80% value, 0.8. Once it hits the 20% value, the time between that 80 and 20% is our fall time or falling slope. Then on the other side, when the output or when the input is falling and it crosses the 50% point, the output will eventually start rising, and when it crosses its 50% point, we now have the propagation delay for the output rising, or T sub PDR for output rising, and that propagation delay again is from 50% input falling to 50% output rising, and the rise time will be as the output is rising once it hits its 20% point, and we start measuring. Once we get to the 80% point, we stop, and that is the rise time, and or also the rising slope. So just keep that in mind as we're going to the following foils. So now let's go through an example of trying to figure out max time and min time, or propagation delay and contamination delay, of a more complex logic block with multiple gates in it and multiple inputs coming in. So we have inputs I0 through I6 coming in on the left side to the gates, and they're coming in at times A0 through A6, where let's say these times are in picoseconds relative to some reference clock edge that's coming in at 0. So A0 is coming in, let's say 20 picoseconds. Let's say these times are in picoseconds. So A0 is coming in at 20 picoseconds after our reference clock. A1 is 30 picoseconds. A2 is 50 picoseconds after that reference clock, etc. The gates themselves, so these NAND gates, NOR gates, and inverters, the amount of time for the delay through each gate, so the time from the input switching for 50% to the output switching 50% is the number provided on the gate itself. So the NAND gate in the upper left is 30 picoseconds from its input crossing 50% to its output crossing 50%. The inverter, kind of in the middle upper, is 20 picoseconds delay from the input to output switching, etc. So we want to find out what is the max time from any given input to O9 and O12, and what is the min time for O9 and O12 to do its switching. So go ahead and pause right here and try to figure it out yourself, and after you start back up, we'll go through this example bit by bit. So if you haven't paused yet, I'm going to start going through example. Go ahead and pause. So I'll start going through the actual determining max delay first. So if we look at the, we'll start from kind of upper left and work our way to the right. So the NAND gate in the upper left has two inputs, I0 and I1. They're coming in at times 20, A0 and A1 of 20 picoseconds and 30 picoseconds. For max delay, we want the longest of those two. So 30 picoseconds is the latest. We add the 30 picoseconds of the NAND gate itself, and so the max delay coming out of that will be timing A7 of 30 plus 30 is 60 picoseconds. So now we'll we only have a single input to the inverter. It's coming in at 60 picoseconds. It has 20 picoseconds through the inverter, so the output of the inverter is going to have a max time of 80 picoseconds. Next, let's go down to the NAND gate below the inverter in the kind of second column, and that has a 2-input NAND gate. One input is coming in at timing A7 of 60 picoseconds. The other one is coming from input I3, coming in at timing A3 of 20 picoseconds. So 60 and 20. 60 is the largest number, so we add that to the 30 picoseconds delay through the NAND gate, and we get an output of 60 plus 30 is 90 picoseconds for timing A10. Now let's go to the NOR gate below that. That has 2 inputs, I5 and I6, which are coming in at timing A5 and A6, both at 20. So both are at the same time. So we take the 40 picoseconds delay through the NOR gate plus the 20 gives us 60 picoseconds. So finally, for the max delay actually at output 09, we go up to the upper right NAND gate that has 2 inputs. One has timing A8 of 80 picoseconds. The other one is input I2 coming in at timing A2 of 50. The largest of those two is the 80. So we take 80 plus 30 and we get our max delay timing for output 09 is 110. For the NOR gate on the bottom driving 012, we have 3 different inputs. A sub 10 is 90. Input I4 is coming in at timing A4 of 20, and A sub 11 is coming in at 60. So between those 3, A sub 10 at 90 is the longest. We add the 50 picoseconds through the NOR gate, and we get 140 picoseconds. So for our max time for 09 is 110, 012 is 140. 09, if we follow back where that longest path came from, it turns out it's coming from input I1 going through the gates that we traced. So the max time from I1, 012, if we trace back the longest times for that one, turns out it's also coming from input I1. So our max time for both 09 and 012 are coming both from I1. Now let's go through the similar analysis for the min time. For min time, if we go back up to the upper left, the first NAND gate in the upper left, we have inputs I0 and I1. We want the quickest of the two this time, so we want A sub 0, which is 20, plus the 30 picoseconds through the NAND gate, gives us a new A7 of 50. We go through the inverter now, and we get a new A8 of 50 plus 20 is 70. And next, let's again go in the same order we did last time and take the NAND gate below it. We want the quickest of its 2 inputs. A sub 7 is at 50 and A sub 3 is at 20. So in this case, the quickest is 20 plus 30 is 50. So A sub 10 is now 50 instead of the previous 90, I think, that we had. Going down to the NOR gate in the middle bottom, we have 2 inputs at 20, 40 through the NOR gate, so A11 stays 60 like it used to be. Now let's go to in the same order we did last time, go up to output I09. We have the NAND gate there. It has 2 inputs. Input A8 timing is 70. The other input, A2 timing, is 50. So the quickest of those two is 50. We add 30 to it, and A sub 9, quickest it is now 80 instead of 110. And for the output 012, we have the NOR gate has 3 different inputs. Timing there is A sub 10 is 50. The middle input is coming from I4, which has timing A sub 4 of 20. And then the third input is A sub 10 of 60. The quickest of those is A sub 4 of 20. We add 50 to it, and we get our min time of 70. So you can see our min time for 09 is now coming from input I2, and the min time for 012 is coming from input I4. And you can see for, in particular, 0 sub 12, that output has a really large delta between its max time and min time, 140 versus 70. So this can go to show you how min time and max time can be actually very different on any given net, depending on the logic cone that you get. So let's just do a quick review of the basics of kind of the RC qualities of transistors in a given process technology. So rather than instead of trying to talk in terms of absolute terms for a given process technology, an absolute resistance value or an absolute capacitance value, and measuring that in terms of microns for a particular device, we've been saying for a given process technology, we want to try and simplify things and say we'll define things in terms of the minimum width, minimum length transistor that we're allowed to draw for that technology, and then put our calculations in terms of that as our basic unit. So if we have our basic unit is a minimum width, minimum length transistor, our value of K for the purposes of this discussion is going to equal 1. If our width of our transistor is 2x minimum, K is going to be 2. If our width of our transistor was 10x minimum, K would be 10. So with that as our basis, our gate cap for a given transistor is going to be whatever width multiple it is, K times our unit capacitance value. Again, is the unit capacitance. The base unit is for a minimum width gate transistor. So the base capacitance value is going to be K times C. The wider you are, the more capacitance you have. Similarly, drain and source cap value is going to equal K times C. And then when we're talking resistance, for a minimum width NMOS, the equivalent resistance is going to be R divided by K. So our unit value of resistance is R. And so the NMOS minimum width is going to have R resistance equivalent. If it was 10 times the width, it would have R divided by 10, because the wider it is, the less resistance, the more current it can draw. For a PMOS, it's going to be 2R times K, or 2R divided by K, rather. And the reason for that is, keep in mind, PMOS has a lower mobility for its carriers than NMOS by about a factor of 2. And so we have to take, it has 2 times the effective resistance of an NMOS. So 2R divided by K. So keep in mind, for a PMOS to have equivalent resistance to an NMOS, we're going to be treating it like it needs to be 2x the width. So the last thing that I want to cover is defining our basic unit of switching delay. So our basic unit of switching delay is going to be defined as having a minimum sized inverter for a given process technology driving another minimum size inverter, assuming that your rise and fall delays are tuned to be fairly equivalent. So if you look at the circuit figure below in part A, you can see we have minimum size inverter is defined as a PMOS that is unit 2 connected to an NMOS that's unit 1 in order to make that inverter. And the reason for that, again, is we want our rise delay to equal our fall delay. So in order to make the PMOS resistance, or RC, in effect, be equal to the NMOS resistance, it needs to be twice as wide. So our unit inverter is a size 2 over size 1 PMOS to NMOS ratio, and it's driving another unit size inverter of PMOS size 2, NMOS size 1. So if we look at just a minimum size inverter, if it was driving no load, so we look at part B there, if we had the minimum size inverter driving no load, we would not have the extra capacitance, the output capacitances that are shown on the right side there, and we would just have our time taken to switch would be proportional to R, whether you're rising or falling. The equivalent resistance of the PMOS and NMOS are both just a value of R, because the PMOS again was 2R divided by 2, so it's just R. So we have our time, rise time or fall time, or I should say propagation delay of rising or falling is going to be proportional to R times the C value of the drain of the NMOS plus the 2C value of the drain of the PMOS. So that's proportional to 3 times RC. And now so that's how much time it would take if you had no load attached to a single minimum sized inverter. If we take a minimum sized inverter driving another minimum sized inverter, we have an additional 2C for the gate of the PMOS device load and 1C for the gate of the NMOS device load. So that would be a time of R times basically 6C. So that's equal to 6 times RC. So that goes to show the difference in delay of an inverter driving no load would be 3 RC, and driving another inverter minimum size is a delay of 6 RC. So just keep that in mind as we're going through the more complex calculations to come.